No questions on homework? All right. All right, so we're gonna talk about some of the properties of these definite integrals today, and then we're gonna get into what are called improper integrals. And so when we do that, when we get to the improper, we're actually going to jump back into chapter 6, and we're going to go to 6.7. Get which one it is. 6.6. And the techniques of integration by parts, trig integrals, all that stuff, partial fractions, that was all chapter 6 in the beginning. So when we do make that jump to 6.6, the integration in that section is going to assume now you have seen all the techniques of integration. So just keep that in mind. The integrals might require a little more effort once we get to 6.6. So let's start out with the properties. Of the integral, of the definite integral. These are things that might make sense, but we can never assume, so we need to state them so that you're allowed to use these. So it's been proven that these are true. All right, so first property is that if you take the definite integral of the function f of x dx, and so we're going, we would say like from A to B. From A to B. It didn't work. Did you talk? No, didn't work. You're still here? I know. No, never mind. We'll talk later. That integral represents what? Geometrically, what is that? That was going to be your quiz today. I decided not to do it, but that was going to be a one-question quiz. Geometrically, what is that? What is it? It's what? It's a function. Well, draw me a picture of what that gives you. Like, no? Okay, so you're giving me the actual fundamental theorem of calculus, right? That equals capital F of B minus capital F of A, where capital F is the antiderivative. Yes, but geometrically, what was that? Like, you get an answer, right? A number. Let's say it's 4. What is it? The area under the curve, right? Basically, the area under the curve between A and B, right? That's the big takeaway from last class. Is what does that mean in a picture? All right. So this property, this first property, says that area is equal to the integral from B to A, f of x dx. Now, what's the difference here so far? I changed these limits of integration, right? The lower limit of integration, the upper limit of integration are interchanged. When you do that, you don't get the same answer, but you get the same answer, different sign. So if the area under the curve between A and B was 4, then if you go from B to A, which is the opposite direction, which doesn't make a whole lot of sense, but if you do reverse the direction, then you change the sign of the answer. Does that make sense? Okay. So that's your first property. The next property, if A equals B, and maybe I should draw a picture over here just as a reminder what I was saying geometrically. What does this all mean? You have some function f, or between A and B. Then we were looking at the area under this curve, right? That right there is the integral A to B f of x dx. That's what that is, right? That yellow area is that definite integral. Now, if A equals B, right? If a equals b, then what do you think the integral, definite integral value should be? 0, right? Because if a is b, you don't have any width, right? So it'd be 0. You have no area. I hope that that seems to be reasonable. Okay, third one. If you try and find the definite integral of a constant, now we know the derivative of a constant was 0, right? Derivative of constant was 0. But the antiderivative of constant is not 0. So let's try and figure out what this answer would be without actually taking an antiderivative, which would be easy anyway, but let's try and figure it out visually. You have a function that is constant, right? Constant flat line. So it starts somewhere, flat line ends somewhere. The height of that is c, agreed? And we're going between a and b. So what would the area under this thing be? It'd be c, right? That's one side of this. We would say this side right here is c. No, it's not that side. Sorry. This side here is c, right? That's the height. And this is a rectangle, right? The area of a rectangle is the length times the width. So I know, or height times the width. I know this side is c. How wide is it? b minus a. b minus a. So this side right here would be b minus a. And so this should be c times b minus a. That makes sense? What's good about that is if, for like as an example, if you had integral, let's say 2 to 5 of pi dx, we don't actually have to sit there and say, what's the antiderivative of pi? Oh, it's pi x, and then take our two things and then plug in, right? We don't necessarily have to do that. All we have to do is say, hey, look, that's a constant. So I know that it's going to be this minus this, right? 3 times this. So 3 pi should be the answer. It's just a quicker way of doing it without having to actually work it out. All right, so that's our third property. Fourth property. We've already talked about this, but I'm going to state it. If we have definite integral, and inside the integrand, that's the thing that we are integrating, is the sum or difference of two functions, then we can split it into two definite integrals and do each one at a time. We did that already, right? When we were actually learning techniques of integration, anytime we had plus or minuses, we could split it up. But remember, this is chapter 5. We were in chapter 6, so I had to show it to you in chapter 6 because we hadn't been through chapter 5. So chapter 5, they're showing it to you for the first time, but we're seeing it again. The only difference is we have the definite integral now instead of the indefinite. All right. Has anyone ever come to my office and seen that? I know a few of you have, and you've seen that that picture I have of a chalkboard that I did a proof on a long time ago. It's the proof of this right here. I mean, we take it for granted that it's true, but that's what it is. 5, let's see. 5, again, we've seen this before. If you have an integral, you have a constant times your function. You can pull the constant out and then do your definite integral. And when you're done with that, you go ahead and multiply that constant through. All right? So constant comes out of the integral, integrate, and then multiply by c at the end. All right, I think all those are pretty natural. I mean, they kind of make sense. The next one, the sixth property, says that If A is less than C is less than B, now I know that's not in alphabetical order, but just bear with me here, right? If A is less than C is less than B, so in a picture, here's what we'd have. Here's A, here's C, here's B, right? Let's say we have a function that does something here, f. Then does it make sense that if you wanted to find the area under the entire function from A to B, that you could go from A to C first and then go from C to B? And split it up into two different, I mean, you could, right? And then add the two answers together? That's what this property says. It says that the integral from A to B of the function should be equal to the integral from A to C of the function plus the integral from C to B of that function. So you're splitting it into those two different areas and adding them up. Add those two, you should get the whole thing. That's a pretty natural result, you think? Makes sense geometrically? All right. We have 9 properties, so we're getting there. The next one says that if your function is greater than or equal to 0 on the interval AB. So what does that mean? If I draw the function, it has to be positive or 0 on some interval. It means it's, when I draw it, it's above the x-axis, or possibly it can touch the x-axis somewhere, but it can't be below the x-axis, right? So if that's the case, then I'm guaranteed that the area under that curve between A and B must also be greater than or equal to 0. So it must be positive. Now this may not seem like a very useful thing, but a lot of times we can't figure out integrals. I mean, I know antiderivatives, I should say. I know that we spent a lot of time trying to figure out antiderivatives of functions, but in reality, if you were to just like close your eyes and put your bag in, or put your arm into the bag of functions and pull one out and say, can I integrate it? The probability of you being able to integrate it by hand is actually 0. This is like a number theory thing or like a measure theory thing. We don't need to get into it, but I mean, really, in real life, we can't integrate a lot of things by hand. Now, the techniques of integration are taught because it's a higher level of thinking. I mean, it's really, that's what it is. It requires more thought, right? Differentiation. I was going over derivatives chain rule last class in my Cal 1, and I mean, chain rule is a pretty easy process to follow, right? Going backwards, we saw, was a lot more difficult. So that's why it's taught. It's taught for that elevated thinking. So what we do with this is we say, okay, I don't know what a function is necessarily doing, and I'm trying to find the area under it. So I try and estimate it with a function I can integrate, and somehow use like a squeeze theorem to try and squeeze the real answer between two things. And to do that, I need to be able to work with inequalities. So I need to be able to say, like, this is greater than something. And when can we say an integral is always positive? Well, the only way we can ever say an integral is going to be positive is if the function itself is greater than 0. If that's true, then that has to be true. Number 8 will kind of lead you a little more into what I'm getting at here. If I have a function f of x that's greater than or equal to g of x on some interval a, b, then how do you think the definite integrals are related? Yeah, the integral a to b of the f function should be greater than or equal to the integral a to b of the g function. And that's how we would use a squeeze theorem. we try and say, all right, maybe we're trying to figure out what g of x is, like this integral. We're trying to figure it out. So we find a function f that's bigger than it, and then the f that we find is something that we know what it does. And so what we can do is create what's called some sort of upper bound on this. So we know that this can never be larger than this particular value. And then we try and get one on the other side that does the same thing, and then try and squeeze the answer between. That's one thing we can do. All right, the last property. Since y'all weren't right out of the gates with the picture idea, let me just draw this one for you. If that's f, I'm on some interval a, b, and my g function has to be below it, or possibly it could touch it, but only touch it and then come back like that. Right? That f is always greater or equal to that g. Right? This f here is always greater than or equal to this g on this interval. Then the area under the red one is greater than or equal to the area under the black one. Yes? That's the geometric idea here. Okay, last thing. If little m is less than or equal to f of x, which is less than or equal to capital M on AB. So I think I'll start this one out with the picture. Now, m here, little m and big M are constants, all right? They're just some numbers. So what we're saying is that on this interval AB, our function is what we call bounded. It's stuck between two numbers, right? So if your function is bounded, then we have some results here. Here's the picture. We have a function. Let's say it does that. Here's A, here's B. Capital M here, capital M, would be any number that's bigger than my function. It doesn't have to be the smallest one that I can find. It can be any number that's bigger. And then little m is any number that I can find that is smaller than my function on that interval. Then what do you think the relationship is with this? Like what do you think I can say about the integral, the definite integral of the function f? What must it be stuck between? Between the integral of this one, right? And the integral of this one? Well, the m is a constant, right? And didn't we say the integral of a constant, you don't have to do the work, it's just subtract and then times. So what should this integral of this one give us? M times, capital M times b minus a. And then this other one should give us what? Little m times b minus a. Big M times b minus a is that area under there, isn't it? Everything there, yellow? That's definitely bigger than the area under the curve, which would be this area, right? Which is definitely bigger than the area underneath little m, which is that one, right? So the yellow is more than the green, which is more than the pink. That's all that's saying. What this gives us is control over what the integral is giving us as an answer. We can somehow say, well, it's between this and this. You know, it'll never be, 10 or whatever. So if we're building something that has to be within a certain tolerance and it comes down to, finding this integral, at least we have some bounds that we can create on that value. All right, that's it for the properties. The next thing I'm going to give you a couple problems in your homework But I'm not actually going to show you an example of this because I think it's too straightforward, but it's something you should see. It's called the average value of a function. And here's the way I'll motivate the idea. If I say take the average of your test scores, right? You just add up your test scores and you divide by how many you had. Yes? Okay, so if I take a function, and let's say I say from A to B, I have some curve, right? And I want to know the average value of the curve. The average value of the curve. Well, what you do is you'd first you plug in A, right? Plug in A and there's a certain height to that. That's a point. Then you plug in the next point. Well, what's the next point after A? I don't know, something right after A, right? What's right after A? There's no number right next to A. As soon as you try and get to one, you missed one, didn't you? Okay, but we won't get in. That again is beyond the scope of this class. But if you put all the different values of the function together, all those dots, you get its graph. I mean, that's what the graph is, right? So if I wanted to take all those values and add them up, what is that? If I add up this height plus every height in there, all of them, what is that? That's the area, right? So I add them all up and I divide by what? How many there were. That's a little subtlety here. So how much is there between here and here? B minus A. That's how many there were, right? B minus A. That's how long this interval is. So all the average value is your normal integral, right, divided by B minus A. That's your average value. So F, the way we write it is F av is equal to 1 over B minus A times the integral A to B f of x dx. And if you look at page 298, look at problems 15, 16, and 17. Those are your homework problems from that. It asks you to find the average value of a function on an interval. So it's just some real quick integration and divide by the length. All right? Now, do you think that a function has to achieve its average value? Look, let's say we take the average value of a function and the average value comes out to be 10. Do you think that somewhere in there, the height of the function must be 10? I'm saying exact, though. Exactly. And so? All right, here, does everyone understand my question first? You're given a function, and its average value turns out to be 10. Does that mean somewhere in there, somewhere between A and B, if you plug in some number, you get 10, and it has to happen at least one time? Make sense that it would, or? Ah, okay. Yeah, so what if it's something like from 1 to 2? Now we'll make it 1 to 3. Let's say the area under here, let's see, how am I going to make this work? 220, so let's say the area under this is 5, and let's say the area under this is 15, which makes this 15 and makes this 5. Do y'all agree with that picture? So my function here is the function that does this. It's a step function like this. Okay, everyone agree that the area under this is 5? The area under this is 15. The total area is 20, and then you divide by the length, which is 2, so you get 10. Does your function ever take on the value 10? No, right? It's 5, and then it jumps up to 15. So there are some restrictions that you have to impose before you can say that. And basically, what do you think it is? If f is what type of function? What? Continuous, right? If f is continuous, then it has to happen. See, this isn't a continuous function. Now, with Cal 1, we would say that this was a jump, right? In Cal 1, we would say that the derivative does not exist here because there's that jump. But in Cal 2, this is actually integrable, meaning you can integrate discontinuous functions. It's possible. I mean, look at it. I can find the area under that curve even though it has a jump in it. It still makes sense. In fact, if I have a curve that does something like this, you know, and I call this A and I call this B, I can find the area under that function even though it's different pieces. So there are different conditions for what it requires to be able to take derivatives and what it requires to find antiderivatives. So it's less restrictive when you're trying to find antiderivatives. So there is a theorem in the book that it's called the mean value theorem. Do you remember in Cal 1 what the mean value theorem said? I'm just going to put MVT, and I'm going to put here Cal 1. The mean value theorem said if you have a function that is continuous, anyone remember? Anyone remember the mean value theorem? I know it's been a whole long time since that, Cal 1. What's mean mean? Average? Okay. So if you connect the two endpoints with the secant line, it has a slope to it, right? The mean value theorem says that somewhere in there, there's a tangent line that's parallel to that line. So there's somewhere in here, I'd say it's probably about here, where if I take the slope of the tangent line, that those two are parallel. That's what the mean value theorem, Cal 1, basically said. You can go back and look it up. But in this class, we have a mean value theorem for integrals. And all it says is what I just said. If the function is continuous, then there is a point somewhere in there where the area is equal to the average. If you look at the average, then that area underneath is equal to the area of the whole thing. So I'm not going to ask you any problems on it, but I'll reference the page. It's right underneath the part that I just talked about. So let me get to it here. Page 297. All right, that's it. We're going to move to 6.6. Any questions? All right, before we get to 6.6, I wanted to review some stuff so that we don't get hung up on it. I mean, I think we're still going to get hung up a little bit, but let's just at least start talking about this before. So I'll just call this some prelim stuff, preliminary. All right. We're going back to Cal 1. If I were to say take the limit as x goes to infinity of 1 over x, you would say what's getting smaller? This is going to 0? Yes, that's true. Because your numerator is the number 1, right? The denominator is getting very large. The ratio then gets smaller, right? So this goes to 0. So I'll just say that this equals 0. But the idea here is that your numerator is fixed and your denominator is going to infinity. And any time that we have that, this goes to 0, right? So please understand that when I write fixed, I mean the number's not moving, okay? The number 1 is just 1, it's not changing. When I say infinity, infinity is not a number. I cannot plug infinity into something, right? But do we all understand that we can think about that this actually means I'm letting the denominator get larger and larger and larger and larger, okay? Yes? We all agree? Because that's the notation I'm going to use in here. I'm going to actually write infinity, but we all have to understand that what I mean is I'm letting that thing go to infinity. All right. Okay, so what about this? What would the limit as x goes to infinity of x to the negative 2 be? Zero? Yeah, because if you rewrite that, x to negative 2 is 1 over x squared. And then we're back in the same boat, right? We have a fixed number over something becoming infinite. It's going to go to infinity. I mean, sorry, it's going to go to 0. It's going to go to infinity on the bottom. So I'll just draw an arrow. It's the same situation as we had up there. All right. How about this? What's the limit as x goes to infinity of sine x over e to the x? What does sine do as you go out, as you let x go to infinity? What does your sine function do? It just keeps oscillating, right? So if you're looking at the sine curve, you're oscillating back and forth between 1 and negative 1. The denominator, e to the x, we all comfortable? E to the x looks like the exponential function, right? It's going to take off to the right, up. So this one's just going back and forth between negative 1 and 1. And then this one is getting bigger and bigger. So what happens? It also goes to 0. Now, the reason why it goes to 0 is similar to the reason why this one goes to 0, except that I can't say fixed, because the top's not really fixed, is it? But we say it's bounded, right? Sine is bounded. Sine is between negative 1 and 1 all the time. Anytime we have a situation where we have a bounded expression over something that's becoming infinite, again, we go to 0. Also, I should point out that on those denominators that were going to infinity, if I would have put negative infinity, it would have given us the same answer. It doesn't matter if it's positive or negative infinity here, because if the top's just staying, you know, between two things or staying and not moving at all, and the denominator is getting bigger and bigger, it does not matter if it's positive or negative. It's going to smash that ratio down to a very small number. It might be a very small negative number or a small positive number, but in either case, they're approaching 0. We good? Okay. How about this one? What's the limit as x goes to infinity of 2 to the x? Infinity, right? Because 2 to the x is like e to the x, right? It goes like that. So this is going to be infinity. And I guess the only justification I have for that is the graph of 2 to the x I know looks like that. So I know that as I go to the right, it goes up to infinity. Now, small, subtle little difference here. What's the limit as x goes to negative infinity of 2 to the x? See, this is where things can get a little tricky. So let me try and do what we call in Cal 1 a direct substitution, even though it's really, really bad to try and plug infinity in, like I said. This is really saying what's 2 to the negative infinity, isn't it? 2 to the negative infinity. But anything to a negative number can be dropped down as 1 over it to the positive. So this is 1 over 2 to the positive infinity. And now what situation do we have? Fixed over infinity. Fixed over infinity goes to 0. Now we could have done that. I heard some people say 0. You could have done that just by looking at the graph, right? Because this is the same graph, 2 to the x, 2 to the x. If I go to negative infinity, now I'm going to the left side. I'm going out here, I'm going to 0. But I don't think that is as useful to know the graph as it is to understand what's happening here. Because a lot of times we won't have the graph of what we're looking at. We just have to understand how things are behaving. Questions on that? All right. That at least, gets our feet wet for what we're going to do now. Now 6.6, improper integrals. Improper integrals. So up to this point, everything that we've done, as far as these definite integrals are concerned, we always said, we're going to fix a function on a closed interval, right? That's what we said we were going to do. We always restricted that function, then we said, oh, we're going to approximate it with these rectangles, and then, add them up and have an infinite number of rectangles, and it turns out to be this antiderivative thing, right? Fundamental theorem of calculus. Great. But what if we want to do something like this instead? What if I'd like to see what happens? By the way, I was trying to find that area, right? Under here. What if I want to take my function, I do want to start at A, and then I don't want to stop. I just want to keep going to the right forever. And I want to find the area forever to the right. Are you going to have, is your answer going to be infinity all the time? What do you think? This is kind of a big deal. Let's think about this. Will you always get infinity? If I say find the area under that function, go to the right forever, will you always get infinity as your answer? Okay. What if I tell you this? The function's always positive. What if I tell you, if I promise you right now, the function that is out here is always above the x-axis? I'm not even going to say it's allowed to touch. It always has to be above the x-axis. Will you always get infinity? Think so? It's one of those very profound questions that we could argue about all day long. We have our opinions. And at some point, we have to turn to the math. Do you understand the question, though? Now, here's the argument that I think you could give. If I told you right now that this function was always positive, and I wanted you to find the area to the right of A forever, here's what I think a good argument would be in support of the fact that that would have to be infinite as an answer, the area. And that would be that if you look at every single rectangle, right? Every single rectangle will have some area to it, won't it? A positive area. And I'm going to add up rectangles forever, right? So I'm always adding some positive number on top of some positive number, and I'm always doing that forever and ever all the way down the x-axis, right? So if I keep on adding positive numbers on top of positive numbers, there should not be a ceiling, right? A maximum. It should just keep, if you say, no, it can't get past 100, eventually I should get past 100, right? but it does not turn out that way, all right? Because if the amount that you're adding each time gets small enough, fast enough, there's two things there. What you're adding has to get smaller, and it has to get small so fast that as you add them up, it just does not get past anything. All right? Let me give you a very simple explanation that will at least motivate you to believe this shit, because I know sometimes it's hard to swallow this pill. Okay. What if I were to take, this is another analogy, take a cup, and it holds 1 cup. All right? Exactly 1 cup. And this is like a perfect scenario. We're not going to get into too much of the details of real life here, so just bear with me. That's exactly 1 cup. Perfectly measured 1 cup exactly, all right? And I sit here and I have another way of measuring, and I pour into that cup exactly 1/10 of a cup of beer. Let's make it beer, right? So we pour 1/10 of a cup of beer in there. And then we come back, and after that, I have a way of pouring in 1/100th of a cup in there. And then I pour in 1/1000th of a cup in there. And then I come in and I pour in 1/10,000th of a cup in there. The question becomes, do I fill the cup up if I keep doing this forever? Do you need to do jumping jacks or something? Go take a walk in the hall, get a drink, come back. You're missing out on some good stuff. Go fill that up with 1/10 of a cup of water, and then 1/100th of a cup of water, and then come back when it's full.
No, it's like that guy who walks halfway there, and then halfway between that, and halfway between that. It's like you never actually get there.
Okay. But think about how profound that is, because I think we would all agree that this is some positive amount of something, right? And this is some positive amount of something, and some positive amount of something, and positive, and every one of these is positive. So we're adding positive and positive and positive. So we keep piling more and more and more and more and more on, right? And the question is, eventually, because you go forever, at some point, does the beer start to flow over the edges of the cup? And again, we're not going to take evaporation into account here. We're not talking about you're thirsty and you're going to drink it anyway, so it doesn't matter. You know, there's a huge sort of debate here. So let's ask again: how many of you think it will overfill eventually? It's okay to go with your gut. Okay, how many of you think that it will not overfill? How many of you think it'll fill it up halfway? 1/4 of the way? 1/10 of the way, right? Okay, so it's a very simple answer to this, all right? Just take this right here real quick. 1/10. 1/10 as a decimal is 0.1, then 0.01, right? That's 1/100th. This is 0.001, that's 1/1000th. This is 0.0001, that's 1/10,000th. And if you add all those together, you get 0.111 forever, which is exactly 1/9. If you take 1/9 and you do old school division on it, right, put 1 in there, division outside of 9, and do that, you get 0.11111 forever. So not only will it not fill up, will it never overfill, you will never exceed 1/9 of a cup if you follow that pattern forever. You'll get closer and closer and closer and closer and closer and closer to 1/9 every time you do it. And if you could do it forever, which you can't, but if you could, you would eventually, because see, you can't reach forever. So you get the idea. We are getting closer to this value, but never past that value. I hope that that somewhat convinces you of what happens here. And so what we're running into with this picture here is that even though I can add up a bunch of positive things forever, it does not necessarily mean that I'm going to always have an infinite answer. And if it is infinite, if it does become an infinite answer, which it could, I will say that that integral diverges. It diverges. Divergent means goes away, right? So we're going to say like infinity, it's going to infinity, it's diverging to infinity, all right? Now, if it does not, and it actually adds up to a number like this one did, and it gets closer and closer and closer to a number, we will say that that integral converges. And the question would be, when does it converge and when does it diverge? What are the conditions for that? What functions do that? What functions don't? So let's just start investigating some simple functions and see when they converge, when they don't, and then we'll come up with some general rules, and then we'll do a bunch of your homework problems, or I'll try to. I've been yapping pretty good up here today, so I don't know how much homework problem stuff I'm going to be able to get to. So let's get some notation established first. If we write, let's say, integral 1 to infinity of 1 over x dx. As a picture, this starts at 1. Where's the function at 1? How high is it? If I plug in 1, I'm up at 1, right? What does this function do as I go out to the right? It gets smaller and smaller and smaller, right? Like this. So this function is definitely always positive, right? As I go to the right, it's always positive. But it's getting smaller, so there is a possibility here that this thing could converge to a number. It could. It could not. Now, if it went up, I'd be done, right? Because it's basically, just adding bigger and bigger numbers as you go out to the right. That's not ever going to converge. So the only difference in what we have here and what we had before was the infinity here instead of a number, right? But the way we compute it is exactly the same. We're still going to find the antiderivative. The antiderivative of 1 over x is the natural log of the absolute value of x. Now, I don't need to put the absolute value of x. Why? Because I'm looking at positive numbers here, right? My x's are between 1 and infinity, so I don't technically need it. And I'm going to go from here 1 to infinity. Now, remember a little while ago I talked about what does it mean to put infinity here? What I really meant was that I'm taking a limit. I'm letting that thing go to infinity. The book actually writes, if you were to look at the book, instead of writing this line here, they would write limit. They would probably use something like t goes to infinity of natural log x evaluated from 1 to t. So that's the way they would do it. I'm condensing that notation into this as long as we understand that infinity is an idea, not a number, right? So let's do this. Let's plug in. If we plug in infinity first, natural log of infinity, then we plug in 1. Natural log of 1 is 0. So we get natural log of infinity. So that's really saying, what does the natural log function do as you go out to infinity? What does the natural log function do? You remember what it looks like? Natural log looks like this. It's the inverse of the exponential function. So it's the reflection of the exponential function over the identity. But as I go out to infinity, where's it headed? It's going kind of slow, but it's going up, right? As I go, it goes up. So this function is going to infinity, which means that the answer is infinity. Which means that this integral is divergent. Therefore, this integral diverges. It has infinite area. It has an infinite area. Is that okay? Next one. Okay, 1 over x didn't get small enough fast enough. So let me try and push it a little bit. How about 1 over x squared? The graph of this looks very similar to 1 over x, doesn't it? Yeah? But because you're squaring the bottom gets bigger faster, and so those little ratios get smaller faster. Is it fast enough that when I add up those areas forever, I converge to something? So let's try it. Let's find the antiderivative. Well, to find the antiderivative, you just need to convert that over into x to the -2, right? Then use your power rule. Your power rule, antiderivative of x to -2 would be -1 over x, or -x to the -1. And we're going to evaluate that from 1 to infinity. Now I'm going to plug in my two values, subtract the answer. When I plug in the first one, -1 over what? Infinity. Okay, I'll come back to that. And then on the other one, I plug in 1. Right? What's happening to this? That's going to go to 0. Right? We just talked about that. We have a fixed number over infinity. That's going to go to 0. So this thing is going to go to 0. And then over here, we have just +1, don't we? So this thing goes to 1. Which means that the integral from 1 to infinity of 1 over x squared dx equals 1, which means it converges. Now keep in mind, we're saying that the area to the right of 1 forever is equal to 1, right? You can't get to the forever, but that's what it's converging to. If you look at it this way, that's a very complicated way to write the number 1, isn't it? You want to use that instead of 1, you could. All right. So let's try another one. That one converged fast enough. What do you think? You think 1 over x cubed will go? Doesn't that get smaller even faster? So that should go, right? It does, but now 1 over x didn't. It diverged. So let's try something. What I'm trying to get at is we've tried the power 1 here, right? 1 over x, and it diverged. We tried 1 over x squared. It converged. I think we all feel comfortable that 1 over x cubed would converge, 1 over x to the 4th would converge. But let's go the other way to the divergent one. It was 1. How can we go the other direction? Instead of going like 2, 3, 4, we go back to, no, y'all aren't with me? I guess what I was trying to get at was this. How about 1 over x to the 0? That's just 1, right? That's just 1? What do you think that's going to be? You have a constant 1 function, right? Forever. That area is infinite, right? Nothing is getting smaller. It's just staying. So this is going to be infinite for sure. This diverges. You could also have used that one rule. Remember, it would have been the constant times b minus a, but what's infinity minus 1? Still infinite, right? 1 times infinity is still infinite. I mean, I'm just trying to get you to think through it, right? No, you can have these different approaches and still get to the same result. But what we will say is it's divergent. It is divergent. So 0 didn't diverged. How about -1? What would I have? I have 1 over x to the -1. That would really be what? Just x, right? And what does the function x look like? The diagonal? And if I go to right forever, it's going to get infinite, right? So I hope that you see that we've kind of narrowed down like when it does converge and when it doesn't. But we haven't taken this one. So I wanted to look at this one. How about 1 over the square root of x? These do get smaller, right? As x gets bigger, that does get smaller. So if you graph this, it is going out the right side. It is tapering off to 0. But is it getting small fast enough? What does your gut tell you? Remember, x to the 1 diverged. X to the 2 converged. This is really x to the 1/2, right? -1/2. We can write it 1 to infinity x to the -1/2 dx. Let's find our antiderivative here. Antiderivative of that is 2 square root of x. Good. Evaluated from 1 to infinity. Is the answer obvious from this now? Plug infinity in, what do you get? Square root of infinity is infinity, times 2 is still infinity. Take away some number, right? Still infinite. This is going to then what? Diverge. Diverges. Because this is infinite. All right, so if we were truly wanting to look at this from the perspective of a math person, right? Here's the way we look at it. We're trying to figure out what's happening from 1 to infinity of 1 over x to some power. Why don't I call that power p for power? And I'd like to know what it does. Like, when does this converge? When does it not? Right? Well, we know right now that there are 2 possible antiderivatives to this. Well, let me do this to help you out. Let's rewrite that as x to the -p. Do we agree? That's the same thing? What are the 2 possible antiderivatives of this? If bless you, if p, what happens if p is 1? It does diverge, but what's the antiderivative? If p is 1, it's the natural log, right? We would do natural log x. That's what the antiderivative would be, right? What would the antiderivative be? Oh, and we would need to evaluate that from 1 to infinity, sorry. Forgot to put that. That's what would happen, right? If this p was a 1, we would say, oh, the antiderivative of 1 over x is natural log of x, and we'd evaluate it from 1 to infinity, and that's what we would do, if p was 1. What if p is not 1? If p is not 1, we have to use the power rule, don't we? The power rule? So what's the antiderivative of x to the -p? It's 1 over -p plus 1, x to the -p plus 1. And then I'd evaluate that from 1 to infinity. All I am doing is applying the rule that we had here. Remember that? The antiderivative of x to the n was 1 over n plus 1, x to the n plus 1. I'm doing that, but instead of n, I have p. So I put 1 over -p plus 1, x to -p plus 1, evaluated from 1 to infinity. We okay with that? Sure? Okay. Now, we already know what happens here because we just did that problem, didn't we? We know that if P is 1, this diverges. Yes? If P is not 1, the question is, what does this do? So I need to go look at that right now, all right? I'm going to take this part right here, and I'm going to go investigate that for a second. I have 1 over negative P plus 1 x to the negative P plus 1. I'm evaluating from 1 to infinity. Now this infinity gets plugged in where here? For P or for X? For X, right? So if I plug infinity in right now, this is infinity, right? Does that mean that this whole thing goes to infinity? Why not? If what's negative? Yeah, that's right. If this exponent is negative, then doesn't that drop that infinity down to the denominator? And then you have 1 over infinity, which goes to 0. So the big question is really, is this negative P plus 1 positive or negative, right? Is that positive or negative? If negative P plus 1 is positive, and let me just move things around here, that means P is less than 1, right? If I just add P to both sides, that really says 1 is greater than P, which is the same as saying P is less than 1. So if this power is positive, then when I plug infinity in, the infinity stays there, right? It doesn't get dropped down. And therefore, this is infinity times a number, and that whole thing is infinite, and it diverges, right? So that would mean, if that's true, then the integral diverges. Now, what if the negative P plus 1 instead turned out to be a negative number, which would be the same as saying that P is what? Greater than 1? Right? Move this P to the other side. So if that right there is a negative number, that means when I plug infinity in, it'll get dropped down to the bottom. I'll have fixed over infinity, which will go to 0. And then that whole thing goes to 0, right? And therefore, it will converge. Yes? Then converges. So, in summary of all of this, therefore, the integral from 1 to infinity of 1 over x to the p dx converges if p is greater than 1 and diverges if what? If p is less than 1. What if p is equal to 1? Didn't we do that already? Right in the very beginning, didn't we? If p was 1, it diverged. So I can come down here and actually say less than or equal to 1, it diverges. You have a question? Ask. It's converges. Yeah. Thank you. Is that right? Converges. What I was trying to show you with those examples and then this final result is the way that we like to approach things when we're trying to, I guess, come up with some sort of conjecture of, is this true or not? So we try a couple of examples each way, and we start to try and see a pattern. Then we say, let's just try and do something in general. And then what we wind up with is a good formula. And now it doesn't matter if If you're faced with a problem, there's not a whole lot you have to do if it's like this. I'll give you an example. What's the limit from, let's say, 2 to infinity of x over square root of x squared plus 1 dx? Bless you. So this is an improper integral, right? We have this infinity there. How are you going to integrate that? Basic u sub. I see something, x squared plus 1. I see its derivative, kind of, x dx. So when I do rewrite this, I'm going to get something like something over square root of u, right? Which is the same as like u to what power? Negative 1/2. Or if we leave it down the bottom, it's u to the 1/2. And so we said if p was less than 1, which it would be, it's going to diverge. So there wouldn't be a whole lot that I would have to do here and just to show that this would diverge. I'll do it though. U is x squared plus 1. I'm going to move fast though. Du is 2x dx. 1/2 du, I'm scaling both sides. I rewrite this as the integral 1/2 comes out 1 over square root of u is the same as u to the 1/2 du. Notice I also lost my limits of integration here, right? So I'm going to show you something that is kind of, well, we haven't done it, okay? I know right now that this falls into the format of this, right? Just replace the x with u and the dx with du. And I know right now that if that p right here is less than or equal to 1, it's going to diverge, which is what I have, right? The problem is, what are my limits of integration? You cannot say 2 to infinity. Why not? Yeah, this was what x was going from 2 to infinity. But that doesn't mean that's what u goes from. So what we need to do is this, is we need to change the limits of integration. I do this very seldom in this class, but I'm going to show it to you because it is a skill that you should have. This right here says x is 2. This right here says x is infinity. Again, we're saying it's infinity. It's possible to do that, but we get the idea, right? So if x is 2, what's u? If this x is 2, then isn't u 5? Okay, so that goes 5 instead. See, that changes? Now what if x is infinity? What's u? Infinity squared plus 1. Still infinity. So this changes from 5 to infinity. Does that change the divergence at all? What do you think? Going from 1 to infinity diverges. Do you think going from 5 to infinity will still diverge? Yes, why? Okay. Think about the area, right? If we have a graph that from 1, yes, 5's out here. All we want is from here on out, right? We know that from 1 all the way out, it's what? From 1 out, it's infinite, right? It diverges. So from here, from 1 out forever is infinite. This from here to here is a finite number, right? It's some number. So if you take the whole thing is infinity and take away, let's say, 2, it's still infinity. So that will still hold. So the answer would be that this diverges. All right, now, still have some time. Start a fresh page here. What if you wanted to do something like this? What if you had an integral yeah, classic example. You have to be a little careful with this. We're going now from negative infinity to positive infinity. So we're trying to find the area under this curve in both directions forever. Okay? We still have the same process though. It could converge, it could diverge. The one thing you have to do here though, to avoid complications, is you need to break this thing up into two separate integrals. One of them needs to go from negative infinity to something, and then this one has to go from that something to infinity. So it's, if you're going to go in infinity in both directions, you've got to cut it in half or not in half, but cut it somewhere, go from negative infinity to that number, and then the next one goes from that number on. The natural number in this case would be 0, right? But you could use 2, you could use -5, you could use pi. It doesn't matter. As long as you pick a number here and here, and then plug those in. Okay. We good? Can we use the thing that we just did? The 1 over x to the p. Can we use that? Do we have 1 over x to the p? Not exactly, right? And that causes a major problem, all right? It does, believe it or not. So because it's not just 1 over x to a power, it's got this 1 plus in here, we cannot apply that. So then you have to just work through this. Do you know the antiderivative of 1 over 1 plus x squared? Of course you do, right? Arctangent. So it's arctangent of x evaluated from negative infinity to 0 plus, the other integral is the same exact thing, isn't it? And that will always happen. Your antiderivative is going to be the same with both. It's your limits of integration that are going to be different. The order here is important. All right, we have to go, when we say negative infinity to 0, you plug the 0 in first, then you subtract what you get when you plug in negative infinity. Then plus, you plug infinity in, and then subtract what you get when you plug in 0, right? So here it is. We are going to do arctangent of 0 plugged in minus arctangent of what? Negative infinity plugged in, plus, now arctangent of infinity, then minus arctangent of 0. Okay, backing up for a second. When I say what's the sine of pi over 4? Sine of pi over 4, you say square root of 2 over 2, right? If I say what's arc sine of square root of 2 over 2, you say pi over 4, right? So when you take sine of an angle, it spits out a number. When you take arc sine of a number, it spits out the angle. Same thing with the tangent here. I'm saying arctangent of 0 means what angle do you plug into tangent to get 0, right? And then arctangent of negative infinity says what angle do you plug into tangent to get negative infinity? So I think a picture here would help. What does tangent look like? Well, here's pi over 2, right? Here's negative pi over 2. And the tangent function is asymptotic there. Remember that? You have these different periods of tangent. There's tangent, then another one over there. So the question is, what angle, or on this axis, on your x-axis, what do you plug in to get 0? 0, right? Plug in 0, you get 0. So I know that this here is 0 minus, now, what do I plug in here to get negative infinity? Yeah, see, so again, this is, the idea is, I can't plug negative infinity in. But what do I plug in to get closer and closer to negative infinity? Well, I have to plug in something that's getting closer and closer to what? Negative pi over 2. Yes? Okay. So negative pi over 2 here. And then plus, again, this one says, what do I plug in to tangent to get infinity? And so I'm coming out this way. That's happening at pi over 2. So pi over 2 there. And then minus, the last one is the same as the one over here, so 0. And so we get pi. How many of you have taken some statistics courses? Where you have these things called probability density functions, where you have a function that the area under the curve, the total area is 1. So that you take all the sums of all the probabilities should be 1. It's kind of like if you take a coin out and you flip a coin, what's the probability of getting heads? What's the probability of getting tails? Well, the probability of the two events together should be 1, right? 100%. You should get either heads or tails. Well, in statistics, we like probability density functions where you take the area under them and you get 1. Because then you have a way of representing all the possible probabilities. All of them add up to be 1. So 100% chance that everything, that any one thing could happen. I don't know if that makes sense. So coming back here, if I wanted to make this a probability density function, all I would do is I put 1 over pi out here. And if I put 1 over pi out here, then this would be a good probability density function because it would come out to be 1 at the end. So the total area under it's 1. There's classic statistics functions that are used all the time that have the unique characteristic of having a probability of 1, or area underneath of 1. All right. That makes sense, this problem? Now, in the beginning of this, I said that there were improper integrals, right? Yes? Everything we've looked at today, okay, everything today, I should have said this in the beginning, are called infinite intervals, or infinite limits. The book breaks improper integrals down into 2 categories. The first category being what happens when you let the interval become infinite, either in one direction or the other, or in both directions. That's what the book calls a type 1 improper integral. Next class, that doesn't mean I'm done, but next class what we'll do is we'll look at functions that we don't go to infinity in each direction, but we're going to look at trying to find the area under a function that has a vertical asymptote in it. And think about even 1 over x again. This is what 1 over x looks like. Right? Looks like that. What if now I wanted to find the integral from 0 to 1? Well, the problem is you can't plug 0 in, can you? It's undefined. So I'm trying to find the area this time in here. And you see how I still have an infinite area up there? So this is what next class will be about, this type of improper integral. And then what we do is we can have an integral that has combinations of multiple, you know, this happening and that happening out that end. But that's next class. So I'm going to now work through a few problems from the homework that I think would be good to show you so that you're prepared for the level of what you'll see. Some of these I'm going to move through quickly, like this one. Anybody have a conjecture here? Oh, wait, that's not 0. Oh, it is 0. Shoot. No, that's okay, because it's defined at 0. That's all right. Right, this is defined at 0? All right. What you thinking? Can you integrate it? Basic u sub. What's your u sub going to be? 1 plus x. What's that derivative there? Dx. You have dx, don't you? This integral now becomes integral 1 over u to what power? 1/4 du. Can you change the limits of integration now? If x was 0, then what's u? 1. If x is infinity, what's u? Infinity plus 1? Infinity. Can we use what we just did in class a second ago? X to the p, right? This is 1 over x to the p. P here is less than 1. This diverges. I'm just going to put since p equals 1/4 is less than 1. You don't have to go through the work. Okay, how about this one? Negative infinity to infinity. Y cubed minus 3y squared dy. What did I say needs to be done if you have negative infinity to infinity? Split it up. Split it up. And how about we go from negative infinity to 0? It just seems like a natural choice, right? Okay, let's take some antiderivatives. What's the antiderivative of y cubed minus 3y squared? 1/4 y to the 4th minus y cubed. I'm going to evaluate that from negative infinity up to 0. Then I'm going to do the same exact antiderivative evaluated from 0 to infinity. Now, I did not mention this last time when we did this example because it didn't happen, but I'll mention it on this one. If either one of these diverges, you're done. You just say diverges. If one of them diverges, that's all you need, all right, is just for one. So I don't know what's going to happen yet, but let's take a look. If I plug 0 in here, what do I get? 0, so I get 0 there. Minus, now let's plug, be careful, negative infinity in. Negative infinity in here. What's negative infinity to the fourth power? Negative infinity to the fourth? It's positive infinity, right? Yes? And then what's negative infinity to the third power? Negative infinity, but then you're subtracting it. So it's plus. So you're getting infinity plus infinity, which is infinity. And therefore, you can stop, because this is going to be divergent. And that's all you need is for one to be divergent, all right? Because of this, there's something subtle about the word divergent that we didn't really get into. And that's when we say it's divergent, we're not necessarily saying that it's infinite. When we say it's divergent, it basically means it's not convergent. Two different things. Convergent means the area is going to a fixed number. Divergent means it's not doing that. Now, if it's infinite, we say it's divergent because it's not going to a number. But it can also mean that it's not going to infinity. Does that make sense or not? I'll give you an example after this to give you an idea of what I mean. But at this point, stop, divergent, done. Let me give you an example of something that's divergent that does not go to infinity. Okay? How about this? Integral 0 to infinity sine x dx. Just think about it. Think about what's happening. So you start moving to the right, you start getting area, right? And then it comes and gets canceled. And then up, and then it gets canceled. And then up, and it gets canceled. So you might want to say it's 0, but the problem is you're never stopping. So as you go out to the right, the area is not converging to anything. It just keeps on, you keep on getting some, and then it goes away, and then it becomes negative, and then, you know what I'm saying? It keeps on going and canceling itself out. Now, if you actually do the computation, the antiderivative of sine is negative cosine, right? 0 to infinity. And when you try and plug infinity into cosine, if you were in a Cal 1 class, this was actually one of my problems on my test, said what's the limit as x goes to infinity of cosine x? The correct answer is this limit does not exist. Because you're saying what does that go to as you go out to infinity and cosine oscillates. So that's not headed anywhere. So what we would say here is it's divergent. Did I make my point? The point I was trying to make was that divergent doesn't mean infinity. If it's infinite, then yes, it's divergent. But that's not the only thing that could happen. Secant, well, that would be a little bit involved, only because secant has a bunch of vertical asymptotes in it. So we haven't looked at those. How about after we look at those, next class we'll address it. But it goes, what, on top and then on bottom and then on top and bottom, top and bottom, top. So if you want to go to infinity, probably going to be divergent. All right. Another homework. We have 10 minutes. Try and pick one that's kind of ugly. Yeah, that one looks ugly. E to the x. Oh, we're going from 0 to infinity. E to the x over e to the 2x plus, we'll make it nice, 4 dx. By the way, your homework, while I'm standing here with the book open, is page 360. It's 5 through 21 odd. And keep in mind, like I said earlier, you're in Chapter 6 now. Techniques of integration are fair game here. All right, so we're going to look at this here. If we look at it, we stare at it enough, long enough maybe. U sub first of e to the x, du would be e to the x dx. Let me try and rewrite this here. The key, I think, to this is realizing that e to the 2x is actually what? E to the x squared. Now, I think I had shown you that once in class before. So what I saw here was I had e to the x squared, and then the derivative of e to the x is up there already. So if I do that and rewrite the problem, the e to the x dx on top is just really du, and I'm left with 1 over u squared plus 4, right? And that right there, arctan, right? You could do trig sub, but you have a formula for this, right? Integral 1 over u squared plus a squared. The antiderivative is 1 over a arctan u over a. So you have 1 over 2 arctan u over 2. Now I have some choices here because I converted this integral, this definite integral into an indefinite integral, and now I have an answer. So if I'm going to put where I'm going to evaluate from, I need to switch everything from the x stuff to the u stuff, don't I? Like I did before. Or I could just switch my u back to what it was. What was u? E to the x, and then just go back to 0 and infinity, which is what I'm going to choose to do here. So watch, I'm going to take this up here, say that this is equal to 1/2 arctan e to the x, that was u, over 2, evaluated from 0 to infinity. What is infinity plugged in here? Well, infinity, e to the infinity is infinity. Over 2 is still infinity. Arctangent of infinity is pi over 2. That's pi over 2 times 1/2 pi over 4. Go with me? Okay, then I subtract from that what I get when I plug in 0. Now be careful here because e to the 0 is not 0, right? E to the 0 is 1 arctan of 1/2. Arctan of 1/2. Dun, dun, dun. Arctan of 1/2. Degrees. If you're in degrees, we can go to radians too, right? Okay, and then times 1/2. Point what? 2 something? 2, 3 something? Ah, now I see. I took this problem from the book and I adapted it. They had +3 here, and I was like, I'll make it +4 to make the arctan easier. But now I realize why they had it, because here, that would have been, instead of a 2, it would have been a √3. And so this would have been 1 over √3 when you plug in, and then the arctan would have been a nice angle. Oh well. I was trying to make this antiderivative nicer. But this is not wrong. It's just our answer is not nice. It's going to be some decimal approximation. Do you understand it, at least the process, though? All right. Well, I believe that's it. Do you all have any questions or concerns here? As far as our timeline is concerned, let's see where we're at. We just had a test, but it seems like there's another one coming up pretty soon. Today's the 7th. We're supposed to start improper integrals next class. So we are ahead of the game, which is a good thing. That'll give us, we might actually have a day to review if we continue at this pace, but we also might get slowed down once we get to chapter 7. So my plan is to finish up 6.6 and start 7.1 next class. Our test is Tuesday, October 28th, the week before, what, Halloween's on that Friday? So I don't, or yes, we do. Yes. Yeah. Oh, yeah. That's the faculty development thing.